All right, so for problem number 16, it says find the electric field at x equals 5 centimeters, and then based on the figure there that we have below, given that Q equals 1 microcoulomb, what position between 3 and 8 has the same for 2Q alone? I feel like we did this one already, but I didn't see the link, so we'll just do it again just in case. So that's part A. Part B is find the position, and part C is can the electric field be 0 anywhere between 0 and 8 centimeters. And then part D, a very large positive or negative values for x, the electric field approaches 0 in both A and B. And which does the most rapidly approach 0 and y? Part E, oh, this is a big question. At what position to the right of 11 centimeters is a total electric field 0, other than at infinity? And then it says use a graphing calculator. That's a little hint. All right, so let's just start with A. So A says find the electric field at x equals 5 centimeters. And let me change the color here. Let's use purple. I'll use purple enough. Oops, that's not the color I want. That's the color I want. All right. So we want to know what's going on here. All right. So remember that there's no charge there, so we are going to use the to calculate the energy, the electric field, not energy. The electric field is equal to capital K constant, and then we're going to plug in the charges. Remember that for the electric field, when we have a point like a test charge, mathematically the test charge cancels out, so we just need the actual charges. So we have a charge here at 3 centimeters, so we need Q3, and it's just Q. I drew my 3 in there, so it's just Q at 3, and then the distance from there to there, which would be the radius, from 3 to 5, which is just 2 units squared. Oops, what am I doing? I'm just going crazy. And so when we think about that, the charge, that electric field will go this way, and then the other charges will go this way, right? Because this is our test charge right here at 5. Okay, so why am I saying that? Well, because this will be, what is that? 6, 7, 8. So charge 8, and then the radius from 5 to 8. And then this would be negative. In other words, these are negative electric fields, and this would be positive, because we're going to the right would be positive, going to the left would be negative. Charge 11. And then we're going to need the distance from 5 to 11. All right, I'm kind of running out of room, but that's okay. Let's do this. Let me slide up a little bit. All right, there we go. Sorry about this. So anyway, when we plug in the numbers, we're going to have 8.99 times 10 to the 9. I'm not going to write the units because I won't have room, times all this stuff, which is going to be 1 times 10 to the negative 6 coulombs, because I got that from, that's what they said Q is, right? So remember that this is micro. Micro is 10 to the negative 6. You guys should probably memorize that by now. And then the distance between those is just 2 centimeters, right? This is given in centimeters, but in meters it's 0.02. And we'll square that. Minus, over here I have 2 times this stuff, so it'd be negative 2 times 10 to the negative 6. All over the distance from 5 to 8, which is just 3 centimeters, or 0.03 meters squared. I'm still going to run out of room here. slide that up. I'm going to slide this over a little bit. And then minus, and then that's just a positive charge. So it's just 1 times 10. Positive charge, the field will be in the negative direction though. And then from 5 to 11, I think it's 0.06, right? Yeah. So 0.06 squared. And so if I plug that in the calculator, I'm going to get 4.0 roughly, 00, times 10 to the 7 newtons per coulomb. Okay, so that's my electric field. That's for part A. So my electric field is equal to that. Okay, and because it's positive, it's going in the positive direction. And most of that is because our negative field with the negative charge plus our other positive is going to sway us in the other direction. And the distance, of course, you know, the fields, the further away you are, the less strength the electric field will have. So the closer you are to the test charge, the more strength you'll have in your field. Now let's reread what part B was. Part B, so that's part A. Part B was at what position between 3 and 8 is the total electric field for negative 2Q alone. So from 3 to 8. And this is a little confusing. So we have A and then we have B. This is saying given figure A. So we're really not even going to focus on. So we're just focusing on this part of the figure now. Okay. And I'm going to erase this because we're going to have to sketch some new stuff, right? So it's saying at what position between 3 and 8. So between 3 and 8, somewhere in there. Will we have negative 2Q alone? In other words, how do I find where this Q cancels with this Q? And I'm just left with the negative 2Q. So let's do this in a different color. So we'll do this in, let's do red. All right, we'll do red. Okay, so for part B, part B is a little more, it's not really challenging. So the total electric field has to have the same value for negative 2Q alone, right? So keep that in mind. We want to end up with negative 2Q, right? Just that charge. That means that the other two have to cancel each other out. And so we're saying somewhere in here, there's a test charge that exists where this and this cancel each other out. If you added those up, they would be 0. And so then we have to think about, well, what's the middle, right? Because they're the same charge, that's good for us because they're the same charge. Remember, this is at 11 centimeters, and this is 1, 2, 3. So the exact middle between those, so 11 minus 3, whoops, is 8. And so I'm going to guess half of 8 in the middle would be 4 units. So that would be 7, right? So I'm going to guess 7. And so if I guess 7, that's the halfway point. And you could crank through the math and figure out what your charge is. And I'll just write it out so you guys can see it. So if I try to calculate the electric field with a test charge at 7, then I get K, right, times, I'm going to have my Q3, so it'd be a positive Q3, and then the radius, and this is why this works, at Q3, so that would be from 3 to 7, And then the next charge would be my 2q, which goes in the negative direction. Negative q, what was that? That's at 8, right? It's at 8. Yeah, 8. Q8. And then the radius from 3 to 8. And then this is going to go in the negative direction, right? And this would be Q11. And the radius there would be from, and I keep writing 3, I apologize. This should be 4, because we're going from, or 7, I'm sorry, it should be 7. So let me erase this. Still stuck doing the old problem. So this would go from 3 to 7. This would go from 7 to 8. And then this would go from 7 to 11. All right, now I'm not going to plug in, I'm just going to plug in what they give us, right? So without doing the numbers, this is still K, but this is just a charge of Q, right? And we're not going to plug that in and convert it yet. This would be 4 centimeters, or 0.04 squared. And then this is minus Q, 2Q over the radius of 0.01. Let me think this through for a second. Yeah, the test charge would go in the negative direction. That would go in the negative direction. And then over here I have negative, and I'm not going to convert it because Q is just Q, right? But the distance from 7 to 4, this is why smack dab in the middle works, squared. And so if you go to do the math on this, what happens is this cancels with this. Those two add up to 0, and you're just left with this charge. So the electric field is based on the charge of -2, but it would go in the negative direction, right? And so that's at 7. So we guess 7. This is the proof. And you crank through the math, plug in K, plug in the charges and the microcoulombs and all that stuff. That would give you the same as the -2Q charge, but it would be pointing, the field would be going in the negative direction. Okay? I don't know if that makes sense or not. All right, let's move on to C. So for part C, can the electric field be 0 anywhere from 0 to 8 centimeters? Okay, so now what they're saying is there a way to make everything balance out between 0 and 8? And at a very positive, a large positive or negative values of X, the electric field approaches 0. Okay. All right. Oh, that's D. Let's just do C first. So I'm going to do C first. Man, this is a long problem. It's like 10 problems in one. Let's do blue now. Oh, I keep doing the wrong marker. All right, let's do blue. We'll do this blue. All right. So for part C, it's saying, can you find an electric field that is equal to 0 between 0 and 8? So I'm going to erase all this stuff here. And so now we're going from 0 to 8. Whoops, went too far. This is 8. 0 to 8. Is there a test charge that lives in that highlighted section that when I do all the charges, it equals the electric field is 0? In other words, I'm going to have some electric fields pointing to the left, and I don't know. I'm guessing that maybe something points to the right, because you got to have some that are a positive charge and the negative charges. And so and basically the electric fields cancel out and they're 0. Or you could have like charges that repel each other. Oh man, that's a tough one. So let me think this through. So I think we could do this without any math. If I have a point charge somewhere over here, right? If I have a point charge that lives somewhere between 0 and 3, that means that this charge would be positive, but it would go in the negative direction. That means that this charge, which is actually negative, also goes in the negative direction. And then this charge here. This might exist, but I'd have to crank through the math. And so one thing that you could do is try it at 0 and try it at 2.99. But I've got to think here for a second. I don't think it would work, because in order for it to be 0, because they're all going in the negative direction, you have to have something that would be in the positive direction. Although this one would be a positive charge, but it's just not going to work mathematically, because this will have a negative charge based on the distance here. This negative charge is going to be way greater because it's the distance is further away, and this one, yeah, it's just not possible here. Now 7 would give us this -2, but the same thing here. So that's one consideration. If it's below the charge of 3, and so I'm going to erase that again. So below the charge of 3, it won't work. So now let's say it lives somewhere over here between 3 and 8. This would generate an electric field this way, which would be positive. This would generate an electric field which would be this way, but you have a negative charge, so your overall electric field would be positive. And then this would be an electric field that would be negative. Mathematically, though, I don't think it would cancel out. Yeah, I don't think there is a place to do it. We'd have to try it all, but I don't think it. What would be a better one is when they repel. So this is actually an electric field heading in this direction, but it would be negative, which would draw this in more. Because this would be technically positive and this is positive, they would repel each other. Yeah, it wouldn't work. So the short answer is no. And you just got to kind of think that one through. So I would say no, you can't. All right, let's work on part D. For part D, at a very large positive or negative value of x, the electric field approaches 0. Okay, so for D, they're saying, okay, now we're going to expand beyond that. Let's do whatever color this is. We'll do green. And I got the right thing. So for part D, it says at a very large positive or negative. In other words, go far enough. How far do you have to go so the electric field approaches 0 in both A and B? What? So now they're talking about both figures. So the electric field approaches 0 rapidly I think, so what they're saying is when this is a tough one. So if I have a test charge that's like way over here that goes towards a very large number, which is basically they're saying that you're going to positive infinity. Well, what happens way over here? Well, this charge goes in the positive direction. This charge would be negative, but the field would want to go this way. So you can have positive and negative charges. And then this charge is also going to go in this direction because your test charge is over here. And so there's going to be a weird interaction between this charge and this charge and this charge. But the further away you get from the charges, Remember that the electric fields weaken and weaken and weaken. So theoretically, as we approach positive infinity, the charge also approaches 0. Okay. Then it says in figure 1848. So give me a second here. I'm just going to go to that figure. I don't think we have that figure. I think they're talking about point B. Yeah, point B. I don't know why they're calling it figure 48. Yeah. I'm saying that because there's a, let's see what this is. Yeah, this one here. So they put down the wrong thing. So for B, let me just go back here. They're saying for A and B. So now they're saying, well, this what happens here for A. For B, the electric field is a little more rapid because if I approach infinity here, because of the charges, and we'd have to do the math on this, this would approach it faster, right? So this is going to go this way, but it's a negative charge. This is going to go this way, but it's a positive charge. So you're going to have some issues here. This is a positive charge, so it goes this way, but it's going to have an interaction here. And then this is a negative charge, even though we're focusing on the test charge, but there's some interactions here. So if you kind of do the math on that, this one would approach quicker. So, but it's no for both. For part D, or I'm sorry, for part D, it's just basically in both scenarios, as x approaches 0. For part A, well, let me label it this way. For part A, as x approaches infinity, right? The electric field approaches 0. For figure B, the electric field, so as x approaches infinity, the electric field approaches 0, and then we would say more rapidly. So it doesn't have to go more infinite. And that's basically it. One last thing for this problem. Man, this is a doozy. Part E, I don't know what color to do it in. Part E, it says, let's pick a color first. Let's do this color. Yeah, that's fun. All right, so we'll do this. So for part E, let me erase all my work here. For part E, it says, what position to the right of 11 centimeters has an electric field of 0? So they're saying, is that for A? Yeah, they don't say it's for A specifically, but when I look at the solution manual, we're dealing with 3 charges at 3, 8, and 11. So they want to know somewhere over here, where does my total electric field equal 0? So there's some proportionality here. So this is an interesting one. What we're really looking for, so let me do the math a little bit. trying to think of how to word this. So I have my charges, right? So I have a positive 1Q, right? And then I have the negative, but that's twice the charge, right? And then I have plus another charge. And I'm looking for a position, and I don't know what that position is. I don't want to call it X because I'm going to use, it says to use a graphing calculator, and I show you how to do it. I'm going to use the variable Y, and so this is our position. Okay, I ran out of room there. Remember that 1 over 0 and these are equal because remember that this, so when we think of this, let me highlight a couple things, and I'm going to write some more information there, but this represents a charge, an electric field charge somewhere, right? And then that charge, we don't know how far away it is, right? And actually, let me back up for a second. Let me back up for 1 second. I don't want Y to be the position. I don't know what that charge is, but this charge is based on the distance from wherever this is, right? So my first charge is at 3, my next charge is at 8. And so I want to know what value of X. So I'm going to arbitrarily have some value of X. And whatever that value of X is, it's going to be, you got to, it's hard to word. You would think whatever that value of X is, it's going to be 3 units away from 0. So you would subtract 3 from it. And so this is our distance, right? So remember that my radius squared in this particular case would be from 3 to X, right? And so then how do I actually find the radius? Well, the radius is just the last term minus the first term. That's how you find that radius, right? Radius equals this. And so that's what we're actually squaring. So if you go back up here to the first one, when we do the math on this, I'm saying 3 centimeters. I go from 3 to 5 centimeters, but we know this value. Well, where did I get that? I said 5 minus 3 centimeters equals 2 centimeters. And then we converted it to meters. So do you see how that works? That's how we find the distance R. And so we don't know what that position is, okay? And then the same thing here. This is going to be X minus 8 squared. And this would be X minus 11. And so Y then equals the electric field. It represents the value for E, the capital E electric field. And so what does that mean? Well, that means that it wants to know when the electric field equals 0. So what we're looking for is when Y equals 0. So I can graph this in Desmos and then figure out when it equals 0. So what I do, and you could, there's other ways you could do that, but that's the quickest and easiest way. So if I go to Desmos, whoops, I got to type in Desmos. Desmos, I don't want the scientific, I want the calculator, the graphing calculator. This one here. And so I'm just going to type that into Desmos. So I'm going to say Y equals, and then I'm going to say 1 divided by X minus 3 raised to the second. And then remember, this is This total charge would be equal to 2, right? Divided by, and then we're going to say x minus 11. Oops. And then we close that, and then we square that. Oops. Square that. Oops. What am I doing? And then we're going to say plus, oops, oops, I did it wrong again, plus 1 divided by, oh wait, this should be 8, not 11. I'm getting ahead of myself. This should be 8, and this is x minus 11. X minus, wrong button, 11, close parentheses, shift, and then, oops, I did it again too. All right, so now this is a weird thing. So we've got let me just make sure I'm plugging this in right. X minus 11, x minus 3, x minus 2. All right, so when you look at the graph, it crosses quite a bit, right? It's saying that at this number, 5 point blah, 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 the electric field equals 0. But remember, the question says past 11, right? So when we look at this thing, the question says to the right of 11. So it's saying somewhere at 5.1, the electric field equals 0. But it's asking us to the right, so it's got to live somewhere over here. So my x value has to be greater than 11. So this is a 0 for sure. Yeah, this is a 0 for sure. And this is a 0 for sure. But I've got to go past 11. Now the tricky part is, where does that occur? When does this cross 11 again? So we got to kind of zoom in and see if it crosses 11 again. According to this, let's see what we got here. This is pretty, oh, see that? That dot right there? That's where it crosses. Now, I knew where to zoom in on that. There's another way that you could do that too. I think if I plug in 0, it'll solve it. Let me try this. I think if I say 0. Yeah, see, when you plug the 0 in, it just crosses right here at this number, right, which is 35.6, roughly. So that's one way you could do it too. So if you do it this way, you get a little bit more precise number. So basically, it's approximately 30.6 centimeters, okay? So that just took a little bit of fancy math. So y equals 0. Oops, I wrote this wrong. So at 30.6 centimeters, y equals 0. Okay, and it would be this. So technically, I would go in there and plug and change that around to meters and stuff, but it doesn't matter because, in other words, this will be 3.06 meters or 30.6. So it doesn't matter if we convert those or not. We just have to remember to convert it back. And I think that's it for that problem. Holy moly, that's a lot. Okay.